Okay, we're almost at 4, so I'll get started. Hi, everybody. I'm Emily Ramey, and I'm a graduate student in astronomy at the University of California, Berkeley. I'd like to thank the BASF organizers for putting together this festival and for giving me a chance to present. And today I'm going to talk to you about pulsars. So first, we'll briefly go over what pulsars actually are, and then we'll talk about some of their history and their discovery in the 1960s. And then we'll go into some of the building blocks of pulsars and what science makes them possible. And then we'll cover some applications of pulsars and why we study them and why they're still important in astronomy today. So pulsars are what's called stellar remnants. They're what's left over when a giant star explodes at the end of its lifetime. And these remnants have very powerful jets of radiation that we can see with radio telescopes. But we can only see the jets when they're pointed right at Earth, which means they appear to be pulsing or blinking like a lighthouse. So you can see an example of this on the right. The animation shows what light we would see down at the bottom every time a pulsar completes its rotation. So there's a big spike when the beam is pointed at us, but otherwise we wouldn't know it was a pulsar because we wouldn't be able to see it. So for another example, here's a real telescope observation of the Crab pulsar, which is in the Crab Nebula. And it's one of the only pulsars that you can see in visible light instead of radio waves. So this is also a pretty bright pulsar. You could actually see this with a small kind of amateur telescope if the conditions were right. So the theory of pulsars was first proposed in 1934 by astronomers Walter Bade and Fritz Zwicky. So they thought that exploding stars would probably leave a very small, very dense core behind them, consisting of particles called neutrons. But nobody had actually discovered these things until 1967, when Jocelyn Bell discovered them as a graduate student at Cambridge. So she was working on an unrelated project at the time. And if you can see that telescope in the background, she had actually helped build that telescope herself. So she was going over all of her data by hand to try and make sure that that telescope was working correctly. And that's when she found this little blip in her data that was repeating about every second when she looked at a certain part of the sky. So she went to her advisor and said, and he said, oh, it's probably just a man-made kind of interference and something that's not from space. But she was able to observe it with another telescope and it was still there. So it wasn't instrumentation and it wasn't man-made. So they had a thought that a lot of us might have had in that scenario, that it was aliens. So they nicknamed it Little Green Men, or LGM for short. But they were eventually able to prove that it was a pulsar. And that led to a Nobel Prize for Jocelyn Bell's advisor. So let's get into the science of how pulsars work. And there are 3 main factors to consider here. So the first building block you need is a supermassive star. And these stars have explosions called supernovae when they die. So for a short time, they give off more light than their entire galaxies while they're exploding. So that's 1 billion trillion times more energy than a nuclear blast. And what you get from a supernova depends on the size of the star that you start with. So if your star is 10 to 25 times the mass of the sun, you'll get a neutron star, which can be a pulsar depending on the radiation it emits. And if it's 25 to 30 times or greater than 250 times the mass of the sun, it will become a black hole. And there's actually a third option between 130 and 250 solar masses, where the star just blows itself up and it doesn't leave anything behind. So we can see in this diagram of the stellar life cycle that an average star like our sun won't become a neutron star. But if it's just the right mass, it's too small a mass to become a black hole, too big a mass to become a white dwarf, it can become a pulsar. And so I'll go into a little bit of how supernovae work, just for some background. So stars are normally supported by what's called radiation pressure, which means that they're fusing a ton of elements together in their cores. And that's creating light, which is heating the material of the star and countering the pressure of gravity. So gravity is constant and never goes away. But the star can't keep fusing elements forever. So once it gets up to iron, the radiation pressure just disappears. So once the radiation pressure goes away, gravity is guaranteed to win, which makes the star collapse on itself and go into a supernova, which is a huge explosion. So after the supernova, only the super dense core of the star is left. And if the star has the right mass, just like in that life cycle we saw before, this will become a pulsar. So the second major factor in pulsar formation is the law of conservation of momentum. When a giant star collapses, it goes from something thousands of times bigger than our sun in some cases to something the size of a small city on Earth, which is tens of kilometers in diameter. So they pack all of their mass into such a small volume that they're about as dense as the nucleus of an atom. So for comparison, if the Earth suddenly became a neutron star, it would only be about 3 football fields across. So the conservation of angular momentum says that whatever energy the original star had from its spin, the neutron star has to have that same rotational energy. But the neutron star is millions of times smaller than the original star. So even if the big star wasn't spinning very fast, originally, when it collapses down, it has to go a lot faster to keep that same rotational energy. And for a real world example, this is what it's like when a figure skater pulls in their arms during a jump. So they're making themselves a little smaller, so they spin faster, and then when they spread their arms out again, they slow down. But with neutron stars, this effect is about 50 to 100 million times stronger. So neutron stars can rotate from about once every minute or so to once every thousandth of a second. So imagine if something the size of a city had to make a full rotation once every second. And the third major ingredient in pulsars is their magnetic fields. So neutron stars are what we call superconductors, which means that whatever magnetism the original star had, the neutron star must have as well, more or less. And this means that, like with the rotation, all that magnetism gets packed into a teeny tiny package, and they become some of the strongest magnets in the universe. So the way we measure magnetism is with Tesla, and the average kitchen magnet is about 0.001 Tesla, or 1/1000th of a Tesla. So if you compare that to a neutron star can be nearly 1,000,000,000,000 Tesla, which means it's 1,000 trillion times stronger than a kitchen magnet. So what all this magnetism does is it makes all the particles in the area move really fast towards its magnetic poles, which are north and south. And these accelerating particles are, we think, what produce the strong jets of radiation. Science isn't exactly sure what produces those jets, but that's our best working theory so far. So a key thing to note is that the magnetic poles of the neutron star are not aligned with the neutron star's rotation. So the jets get swept around in a circle as the neutron star rotates, and that's why they seem to be blinking on Earth. That's why we get that lighthouse effect. So what's the purpose of knowing this? Why are pulsars important in astronomy today? One reason is that they have really extreme physics involved, so we can't make any objects on Earth that are as dense as a neutron star or as highly magnetic. So we just have to study them from a distance and try to find out what happens when you reach those densities or magnetic field strengths. So the major use in astronomy is something completely different. Pulsars are incredibly stable rotators. So there's no matter in space to slow a pulsar down or get in its way. So they keep the same exact rotation rate for sometimes millions of years, and they can be timed with really incredible precision on Earth. So the pulsars are more accurate on longer timescales than the best atomic clocks, since atomic clocks tend to start to degrade over time. And this reliable timing can be used for all sorts of things, like checking atomic clocks for accuracy, testing improved theories of gravity, and searching for gravitational waves. So a little bit more about gravitational waves. That's kind of the hot topic in astronomy right now. So there are 2 ways to detect gravitational waves. The first is indirectly. So many pulsars are in binary systems, which is when they're orbiting each other, they can create gravitational waves. So even though there's no matter in between them normally to affect their orbits, the energy for those gravitational waves has to come from somewhere. And when the gravitational waves leave the system, they're taking energy away. So where that energy comes from is the orbit itself. So as the gravitational waves take energy from the system, the pulsars start to get closer together and the rotation rate speeds up, which is what we can measure with pulsar timing. So here's a little animation of this. the two neutron stars get faster and faster. They get closer and closer until finally they collide in another supernova. So we've actually already been able to confirm this with observations, and we have indirectly detected gravitational waves from systems like this. But the second type of gravitational wave detection is direct detection, and that's a lot harder to do. So when a gravitational wave goes through a pulsar, it kind of jiggles it a little bit closer to us or a little bit farther away, like when you're swimming in the ocean and a wave goes past. So that causes the blinks from the pulsar to be just a little bit closer together or just a little bit farther apart than they would be normally. And this leads us to pulsar timing arrays. So that's where we measure many different pulsars from all around the galaxy to try and give us a map of where the gravitational waves are. So this isn't to detect the smaller gravitational waves like from the pulsars before, but these gravitational waves would span our entire galaxy. And these types of gravitational waves would actually come from mergers of supermassive black holes. So they're harder to detect, but it would be really interesting for astronomy if we did detect them. So we haven't seen any observation of these so far, but our instruments are always getting better every year. So scientists are very hopeful that we will be able to detect them in the next decade or so. So in conclusion, pulsars are very dense and energetic remnants of huge stars that have exploded. They have very fast, very stable spin rates, and they emit powerful jets of radiation, which is why we can use them as timers to some extent for other things in astronomy. And they can be used for a lot of cool science applications, such as in quantum physics, atomic timing, or the detection of gravitational waves. So pulsars are cool. If you take one thing from this presentation, take that. And thanks everybody for coming to this talk. I will take questions in the Q&A now. So post a question if you have it. I can answer the ones that were posted during the presentation. So the first one is, how many elements do stars use in their core? And I don't have an exact answer for that. They start with hydrogen and then they go to helium. And then after helium, they go to carbon. But there are lots of other elements that kind of get fused along the way. So yeah, however many elements are up to iron, that's how many elements that the star goes through before it gets to iron. One other question is, do pulsars have a life and die? Which is a really interesting one, actually. So pulsars do have a kind of life cycle. They never really die exactly. They don't just go away, but they can stop spinning eventually after millions or billions of years. They kind of slow down in their spin rates. They lose some of their magnetism, and they become too dim for us to see. So that kind of would be a death to us because we couldn't see it anymore. But they wouldn't ever explode really on their own. One other question is, what happens to stars with masses between 125 and 250 solar masses? So what happens between 125 and 250 solar masses is actually that you get a different type of supernova than you would get with a different mass star. So it's called a pair instability supernova. And it involves some kind of complicated processes in the core of the star, but it just basically ends up with the explosion of the star being too violent for any core to be left. Yeah. And another question is, why do stars jump from helium to carbon? So the reason that stars go from helium to carbon has to do with the atomic numbers of those elements. So helium nuclei each have two protons in them. And so you need helium-4 to make carbon, which is 2 protons and 2 neutrons. And then once it gets hot enough in the core, the star starts to be able to fuse two helium-4s into a carbon, carbonate, I think, no, some type of carbon. So once it gets to enough pressure, those helium-4s will be the dominant elements reacting and turning into carbon. So there isn't really a way to get something with 3 protons, which would be lithium, because that would, you would have to combine 2 elements into one, and so it would have to be an even number of protons, barring some other chemical processes. Okay. So let's see. Other questions? So somebody says, I read something about a millisecond pulsar and I want to know what it is. So a millisecond pulsar is basically just a pulsar that is spinning at a rate that is once every millisecond or so, which is 1,000th of a second. So it's not super different from other pulsars, except for just that its spin rate is really fast. And the fact that its spin rate is really fast gives it a little bit more stability than a pulsar whose spin rate is really slow. And the reason for that is that the bigger pulsars and the ones that spin slower actually undergo something called star quakes, which we don't really understand what they are, but they're kind of sudden changes in the rotation of a pulsar. They're not very frequent, but they're small changes in the rotation of a pulsar, and we think that's because the neutron star is undergoing some sort of contraction on itself. And you don't really see that with millisecond pulsars for some reason, but you see that with pulsars with longer periods. And so we tend to use millisecond pulsars for timing rather than longer period pulsars. Okay. So somebody asked, when 2 pulsars collide, do they form a bigger pulsar? And the answer is no, so pulsars are actually in this sweet spot of mass where they're not quite a black hole, but they're not a white dwarf, they're not a star of their own. So we think that about 1.3, 1.4 solar masses is the tipping point for a star to become, for a neutron star to become a black hole. And the star that's undergoing a supernova is going to have a mass that's many times that. But you can't get a neutron star from any supernova explosion that's bigger than about 1.3, 1.4 solar masses. And so when 2 pulsars collide, the theory is that they'll either form a black hole or they will form, or they won't form anything. They'll explode and they'll blow each other apart. So have we found any pulsars in multiple star systems with more than 2 suns? So that's an interesting question, actually. The short answer is yes. Yes, we have. So sometimes stars will be orbiting each other, and one of those stars will become a pulsar. It'll have a supernova and it'll become a pulsar, and the other one won't. And what happens is, if they're in close enough orbit, the pulsar actually starts stealing. It starts stealing mass from the other star. It starts stealing its outer layers of hydrogen. And so this can form what is called a type 1a supernova. And a type 1a supernova is when you have, oh, never mind, sorry. A type 1a supernova is when a white dwarf is stealing from its companion. But you can also have the same kind of thing with a neutron star. where the neutron star is stealing mass from its companion star, and it gets enough mass from this where it has a supernova of its own again and becomes a black hole. We have another question. What happens when a black hole and a pulsar meet each other? Would the black hole just suck it in, or would both pass each other? So it depends on what the trajectories of the two are. So a black hole, it doesn't necessarily suck anything in. It's just a matter of what is on a path where it's going to collide with the black hole and pass the event horizon. So other than, if you're not close to the event horizon, it's just a massive object like any other. So if the neutron star was on the right trajectory, it would just orbit the black hole, and it would have a stable orbit and it would never get sucked in. But if it were on a collision course, basically, if it had an unstable orbit, or instable orbit, sorry, then the black hole, I think, would combine with the neutron star, basically. So we've never observed that happening, so we don't really know exactly what would happen. But there is a point at which nothing can escape from the black hole, even light. And so I don't imagine that a neutron star would be any different than that. And it might cause some sort of new type of supernova where they would either, both, just both annihilate each other and leave no remnant. But yeah, it would be hard to verify something like that at this point. Another question, I know pulsars emit X-ray and gamma rays, but do they emit ultraviolet and radio waves? Yes, so pulsars do emit radio waves. That's actually the primary way that we detect them. We find that most pulsars emit in the radio part of the spectrum. They can also emit in other parts of the spectrum, like the Crab pulsar. That's an optical pulsar, and they can emit in several parts of the spectrum at once. So sometimes you'll see a pulsar emitting radio waves, and it's also emitting gamma rays, but just with different processes for each. So they can definitely emit radio waves. I imagine some emit ultraviolet waves, but not probably as many as we can detect in the radio waves. Another question is, how much time do pulsars spin, or do they keep spinning? So let's see. The lifetime of a pulsar would be, if I had to make an educated guess without looking it up, would probably be several billions of years. So there is definitely a spin down rate for pulsars, but we can quantify the spin down rate. We can say, oh, it's spinning at this speed and it's slowing down spinning at this speed, basically. So it's different for each pulsar, but I would say that like some sort of average among the pulsars we found is billions of years to stop spinning altogether after formation. And we do see some pulsars that are, or we do see some neutron stars that aren't pulsars. So those either have completely spun down or they were never pulsars to begin with. And it's an interesting kind of field of inquiry of where do these neutron stars come from that aren't pulsars, and have they just come from pulsars and died at the end of their lifetime, or were they formed in some different way? Let's look for other questions. So if pulsars never end, why aren't there more pulsars than anything else? So that is a good question. It's because the formation of pulsars is relatively rare. So there aren't very many pulsars being created to begin with, and the universe is a really huge place. So yeah, there are more black holes being created than pulsars based on the way the mass distribution works. And so black holes actually, unlike pulsars, it's theorized that black holes eventually kind of die and there's nothing left of them due to them emitting a certain type of radiation, which Stephen Hawking theorized. Other questions? So can a pulsar steal enough mass from an object that when the supernova happens, the supernova leaves behind a pulsar? So the short answer is no, because pulsars are already kind of the last step before a black hole. So if a supernova happens to a pulsar, it's either going to leave nothing behind or it's going to leave a black hole behind. So there wouldn't be a supernova unless the pulsar had gotten enough mass to become a black hole. Let's see. Here's another one. How did our Earth get so many elements? That is a rather long answer because all of the elements on the Earth came from different places. So when the universe was formed, basically, there was only hydrogen and helium, or yeah, hydrogen, tiny little bit of helium, but mostly hydrogen. And the way that stars formed actually is because of little tiny instabilities in the hydrogen that caused it to clump together and be compact enough to start nuclear fusion, which formed the first stars. And there's a lot of research into what those stars were like because we know they were very different from the stars we see today. They were more massive and they had probably some different processes than we see in stars today. Oops. So some elements were formed in the cores of those first stars. Some elements are formed in the cores of stars today, up to iron, basically. And so anything with an atomic number higher than iron actually was formed in a supernova or by the solar winds of certain types of stars. Yeah, so certain types of stars can have solar winds that can actually form different elements. We think it's theorized. Yeah, the name escapes me right now. I should remember this. Yeah, but definitely certain types of supernova form certain types of elements. And yeah. I guess we're about 2 minutes from the end, so maybe one more quick question. So this question is, what makes a black hole? And basically, it's the same process in theory as what makes a neutron star. So the star can't fuse elements anymore. It's gotten to iron, and that's the kind of stopping point for a star. So gravity crushes in, it causes the star to fall into its center really quickly, and it rebounds into an explosion. And so the center keeps collapsing into a really dense, compact object. And sometimes, if that doesn't have enough mass, that's a neutron star. And then if it has more mass, then it becomes a black hole. And a black hole has so much gravity that even light can't escape it at a certain radius. So we don't really know what is in a black hole because there's a certain point at which we can't get any more any more light out of it. We can't get any readings in there. There's no probe that we could send that could come back because even light can't escape it. Yeah. Thank you everybody for your questions and for coming to my talk. And I will say goodbye now and turn it back over to moderators. Bye.
Thanks everyone, and thanks Emily. I'm so glad you could join us this afternoon, and hope to see you at more events tonight or Saturday or Sunday. Thanks. Bye.